Well, Erica will start the recording. Welcome, everyone. And my name is Mary Dussault at the Smithsonian Astrophysical Observatory. Thanks for coming to webinar 2 in our series for the NASA's Universe of Learning Smithsonian Affiliations Partnership. Also on the line are Tim from Space Telescope Science Institute, Brandon also from STSCI, Erica, and also today, if you go forward, Natalie from Smithsonian Affiliations headquarters on the line. Natalie, did you want to say hello or any words for our group?
Good afternoon, everyone. I just thank you all for joining us again today. We are, yes, like Mary said, well on our way with webinar number 2. So once we get to that end, I will definitely be helping you all navigate the application process and awards. So back to you.
Great. Thanks, Natalie. And today, our guest subject matter expert is going to be Dr. Gabriel Brammer from the Niels Bohr Institute at the University of Copenhagen. And he'll be on the line. Gabe, I think you're on the line now. I just want to make sure we can hear you.
Yep, I'm here. Hello.
Good. Great. Good. All right. So, again, this is starting a 2-webinar cluster of the big question, how does the universe work? Today we'll take a little tour of the universe in space, really, and then we'll find out that that's connected to a tour of the universe in time. And next week we'll be talking about the universe in color. And so specifically today, we'll start with Tim presenting the resources that are related to this question of what's our place in the universe. We'll get I'll present a little bit on the history of human ideas about the universe, and we'll take a tour of the visible universe. Dr. Brammer is going to talk to us about the very farthest galaxies and stars that are visible, and then we'll end with questions and next steps. But again, anytime through the whole webinar, if you have questions or you want something explained again, please use the chat. Erica will be monitoring that and make sure that those questions get answered. Okay. So, Tim, I think an introduction to the resources related to our topic of the day.
All right, so we have a number of things that we're going to show you today. Giving people a mental map of what is out there, what the universe is made of, is something that's going to be really helpful no matter what you're touching on beyond the solar system. There's a lot of misconceptions, and Mary will be touching on those today as we go through. First off, I want to mention the Visions of the Universe exhibit. This is a free, already produced exhibit that you can use. There are some online high-res PDFs that are intended for a professional print center. You can use them in an exhibit. You can build an activity around it. There is a supplemental booklet that's available for each poster that gives an overview of the exhibit, the science background, the science misconceptions. There's a glossary, related educational resources, all sorts of things for you. Also, if you're interested, there are physical exhibits available as well. The last time I checked, we had about 12 copies. There are 6-foot high floor panels. You'd need to pay for shipping to your site and back, but otherwise they are free for you to use. Just let one of us know and we can hook you up with those. And if you check that website there, you can see some more details about all of those. Next up, I'm going to mention Astro Pics, as we almost always do. If you want to find something in the universe, Astro Pics is the way to do it. And let me shrink this down so I can pull Astro Pics up. There we go. So yes, it's possible to do a search for anything you want. Say you want Pictures of nebula, so you can explain what that is. Well, we've got all sorts. Carina, if I expand my thing, oops. If I scroll down, we'll be able to see more. We've got the Eagle Nebula in here, um, all sorts of wonderful things that you can find. I'm actually going to point out one other thing. One lovely thing that you can do once you pull up that image is you can, if you hover your mouse over, you can pull up some, a little zoom in and get some more detail. So there's this lovely galaxy here, known by the name of NGC 5949. Those official names are really descriptive. But like many of the galaxies out there, if you look in the background, you may be able to see some other galaxies kind of hanging out behind it. Anything we're looking at is just one little slice in the whole universe going back. So it's often a great thing to look forward and back in these things as you're going along. All right, back to the slides. We want to make sure that you've got a connection to, Mary's going to be talking about the history of some of the astronomy and the discoveries in there. There's an astronomical photographic plate collection online, and you can see some of the women in astronomy at the Harvard College Observatory. These are some of the women who've studied and curated over 130 years of the night sky, all preserved on glass photographs, glass plate photographs, as it says on the site. Those are available for research. Many of those glass plate photographs are becoming available online. You're going to hear a little bit about Henrietta Leavitt and some Cepheids today. You can go through, if you go to this website, there's this little portal called Dash, and you can go in there to access those. So please feel free to check those out. I also want to point out that there are a number of videos available that you can use both for you or your own staff's education, or you may be able to find a way to adapt these into some activity happening on the floor. Beyond the Solar System DVD video series is one set of videos. This was produced by the Harvard Smithsonian CFA, Mary and Company. They were originally on DVD. Now they are available online through the magic of the internet. There are a number of key concept videos and evidence videos. Things like Our Universe is Made of Galaxies, How Do We Know the Age of the Universe? And then there are some research videos. Hiranya Paris, don't know if I'm is that right, Mary? Thank you. And The Big Bang, and lots more. And I'm going to show a clip of part of one of these. And I'd like you to think, as you're watching through this, how might you be able to use this with your audience? And I'm not sure if the sound is going to come through or not. We'll find out. We're not going to watch the whole thing either. I'm going to jump. Is there sound, Mary?
There's no sound. No.
All right. So it's talking about passing through an ocean of stars and how many of these stars have planets just like our own. And as you travel further out, those stars are grouped into giant spiral arms. And it shows an artist's impression of the Milky Way Galaxy. Oops. So by the time you get to this point of view, the individual stars are no longer visible on their own, but each bright point is a group of thousands of stars. And you'll see a little bit about how this hierarchy of the universe can form into a mental model as Mary goes through today, but maybe that is something that might be useful for communicating that with your audience as well. All right, I have two other videos here. These two were created by some folks down the hall from me here at the Space Telescope Science Institute. One was used to make the IMAX film Hubble, Galaxies Across Space and Time. Both of these are available for you to use. They're online, and if you check out the Goddard Visualization Studio, svs.gsfc.nasa.gov, lots of acronyms because it's NASA. You can find these and many, many other visualizations. So I'm going to play both of these, and they should both play at the same time while we're going along here. There we go. So these are both some concepts of flying through space, seeing the numerous galaxies that are around and getting a three-dimensional sense of how they are laid out there. When we look at a photograph, it's just a 2D picture of the universe, but there's actually three-dimensional space in there, and that's a really tough connection for a lot of people to make. Plus, these are just really cool to watch.
Yeah, they really are.
And as always, all of these slides will be posted after the webinar, and the webinar is recorded. So if you want to pick up these links there, feel free. Don't worry if you haven't been able to scratch down all of those numbers, or if you make a typo, you'll have access to it afterwards. I'm going to bring up ViewSpace as well. This that you're seeing is a brand new design for ViewSpace, which is going to be launched in not too long, so we're looking forward to that. But ViewSpace has interactives and videos. They are available for any informal learning site, museum, science center, historic house, whatever. If you wanna show these off, it's effectively an exhibit that can be installed. It's completely free. There's looping video. I think there's like 11 hours. You're not going to get tired of watching this stuff. Gorgeous imagery, accessible science. And if you go to viewspace.org, you'll be able to request, you have to request an account, and we'll give you access, and then you'll be able to play them to your heart's content and even set them up in front of your users, and we'll provide some support on being able to do that too. But Mary's going to show you a clip of one that we're about to release, or at least some screenshots from one that's going to be released in the next week or two once we get some image permissions. All right, couple quick things. Night Sky Network guides and toolkits, our galaxy, our universe. The toolkits consist of a manual with plans for activities to explore what the universe is made of and scale models. There are also videos that are available online at this link that model how to go through questions and answer sessions with others. Night Sky Network has a number of toolkits and activities like this. And they're accessible through outreach resources at the top of the page. It's not NASA, but it's NASA-funded project made by a network of amateur astronomy clubs, and the creation of most of these, yeah, I already said that, the creation of most of these outreach resources were funded by NASA. It's a fabulous program, and we will refer back to a couple activities within these toolkits a couple times through the webinars, because there's some really cool stuff in there. Oh, there's also, I just threw a link in here. There's a printable or an online tour of how big the universe is, created by the NASA Smithsonian Education Forum. I'll let you check that on your own so we can keep moving. And I wanted to mention the cosmic distance scale. This is also connected to this idea of how far away things are, how big they are in comparison to us, that we're going to be exploring today. This is created by some folks at NASA Goddard. And it doesn't use scientific notation, which is actually kind of nice when you're working with the public, because you can just see how many zeros there are going on to really get a sense of how big they are, because the numbers physically get bigger. And last piece, there are some women in STEM posters. If you're looking for more information on folks like Henrietta Leavitt, Carolyn Herschel, some of the other women who've been involved in STEM, beyond those, these posters are a really cool resource. You can build activities around them. You can put them up just as wonderful decorations for your hall, all sorts of other things. So with that, I'm going to pass it back over to Mary and let her take it away from here. Did you want to grab control of this as well, Mary? Or I can run the slides.
I think only because I want to show that ViewSpace
All right.
movie from my hard drive. So I'm going to take over here and get to the slide we're on and present. So,
all right.
And now I should be
yep,
there.
you're good.
Is that correct? All right.
Oh.
Uh-oh, did something happen?
You're back at slide 1, just advance a bunch.
Oh,
You'll get there.
Okay. All right, sorry. Yeah, there we go. Just see if I can get forward here. Okay. Well, as Tim's tour of some of the resources that are involved shows, there's lots of opportunities to introduce your visitors and your audiences to these ideas of the universe beyond the solar system, which is really the realm in which NASA's universe of learning plays. This is where all the research from the Space Telescope and the astrophysics missions are exploring these big questions about our place in space, our place in time. And these are ancient human questions. And one of the things I happen to have a personal interest in history of science, and I know that many of you are from institutions that are multidisciplinary in nature or non-science disciplines. So I like to start with our tour of the universe with a tour of kind of historical human ideas about the universe and maps. This is actually a clay tablet that's about 5,000 years old, which is some of the oldest maps that kind of tried to place our human society in the context of the bigger world, and we're still doing that at NASA. And of course, another really great entree into these big topics is through the fact that many cultures all over the world have questions about our place in the universe, and ideas about that are not just part of the Western science tradition. They come from pretty much every continent. On the left side of this slide is I think it's 11th century Chinese map of the sky, and I don't know. Let me see if I can get an annotation pointer here, just so I can. Can you see my mouse?
Yes.
My cursor? Yes. Okay. So, so this is the Milky Way here. This path on this slide, and if you were to really look close, you end up seeing some familiar constellations and some not. The middle picture is an image of a Mayan temple in which this arch represents the Milky Way. So that's a feature in the sky that is part of the understanding what that big band of stars is we have different ideas now from the knowledge we get from space telescopes, but that story, creation stories and origin stories have been informed by our knowledge of the sky in every culture. And so that's a representation of the Milky Way. On the right, this is actually an image. Another interest of mine is women in astronomy. And the picture on the right is from Hildegard of Bingen, who was a nun and polymath, really did a lot of writing and in 11th century, and this represents the kind of a model of the universe at that time. So you have Earth at the center, and you have the planets here, Mercury, Venus, and the sun is out here. I'm trying to remember because, of course, this was where Earth is at the center, and the firmament of stars outside. So here's a particular model of the universe. Other cultures also viewed phenomena that are now part of NASA astrophysics. So this is another kind of entree multicultural astronomy into the world of current astrophysics. The life and death of stars we'll be talking about in later webinars. And in 1054, cultures all over the globe, including the Chinese, and hypothetically the Anasazi. This image on the left is from Anasazi wall painting, and it's been theorized that this represents this supernova explosion in 1054 that now we see as this image on the right. So certainly multicultural astronomy and entrees into big ideas and concepts that we're talking about is a great way to engage audiences. A little earlier, Tim highlighted the view space as a resource from NASA's Universe of Learning that is continuing to produce new content. And I think right now they're producing this view space segment about multicultural astronomy. And it includes highlighting, as you see here, Polynesian and Hawaiian and Lakota star knowledge. I'm going to try to play a little clip of it here from my computer and see if it translates over my my somewhat suspect wireless. If it doesn't, let me know, Tim, and I will just stop. All right, let's see. And are you hearing the?
Yes, we are hearing it.
Good.
Very, very slightly in the background. Yes, and it's quite faint. It's just some background music, though. There's no narration or anything going along with it, so you're not missing out too much.
So at any rate, the as Tim mentioned, the view space content, which you kind of provide the equipment, and he can, is a great way of accessing NASA's Universe of Learning content. Let me get back to the slideshow here. All right. And here's some screenshots from that show. So more recently in history, it's really the invention of the telescope that started enlarging our view and giving us the tour of the universe that I'm about to take you on. So before the telescope, limited by the human eye, there was still plenty to learn about the stars. Measuring, making predictions, and even, but it's of course the invention of the telescope and the use of the telescope to observe the heavens, where some of Galileo's observations started realizing, providing evidence for the idea that the Earth may not be at the center of the universe as Copernicus had hypothesized. And so that evidence is in that Visions of the Universe exhibit, from things like Saturn having these weird ears to Jupiter having moons that go around it. So not everything revolved around the Earth, certainly. And so as telescopes got bigger, new discoveries, and we're able to collect more light, and these days more colors of light. With new technology come new discoveries, and that's another theme in the NASA's Universe of Learning, this idea that of how we know, and that sometimes technology drives new discoveries. So here's a picture of William Herschel's telescope back in the 18th century, and a map of what Herschel believed to be the structure of the entire universe based on the measurements of brightnesses of stars that he made using the telescope. Also discovered Uranus, kind of the first new planet past the ones known by the ancients. And you'll see as this strange gap here has to do with not being able to see many stars in that direction. And if you remember the clouds of the Milky Way, we now know that there's kind of clouds obscuring what's beyond that. So Herschel's measurements, which were very accurate, were not only his own, but were supported by the work of his sister, Caroline Herschel. And in fact, to this day, the detailed observations of the positions of stars are part of catalogs of stars that astronomers still use. And so from Hildegard of Bingen through Caroline Herschel and women's contributions to astronomy and the contributions of other scientists from underrepresented groups are another way to make some of the science ideas accessible to more people. One of Caroline Herschel's discoveries actually was she started noticing that these fuzzy things, which were called spiral nebula, and William Herschel ended up taking over, looking for these spiral nebula and making catalogs of them. And this was a big source of new understanding about what's out there in the universe. The question of whether these spiral nebula were inside, were star systems being formed, or what were these? This was a question that was unknown. Over here you can see this is the Earl of Rosse's 72-inch reflector. So it's a telescope that was so big it could only look in this one direction because you couldn't really turn the whole thing around. So telescopes started to get big and unwieldy, in fact, without new technologies here. But as I said, this question of the spiral nebula, it was only when you started being able to take photographs of through the telescope, with the invention of cameras and putting them on the ends of telescopes and being able to record, you started to get these photographs of these spiral nebula. And this was a great debate into the early 20th century, actually. In fact, coming up in 2020, we'll be on the 100th anniversary of the great debate between Harlow Shapley. I'm sorry, I'm having maybe Tim I'm having a neuron lapse. Curtis, about the nature of these spiral nebula and whether they were inside our own Milky Way, systems inside our own Milky Way, or island universes far away from the Milky Way. And the solution to this question of the structure of the universe and how far these things were away really couldn't come until we had a way to measure the distances, a really good way to measure the distances to stars. And in the lower right here, there's a picture of Henrietta Leavitt, who was one of the Harvard computers, as they were called, women that were hired to make measurements on these new glass plates. And Henrietta Leavitt noticed that she made some key discoveries about a particular kind of pulsating star that allowed her to determine that the rate of these Cepheid stars was actually related to their intrinsic brightness, so they became standard candles for measuring distance. And so Edwin Hubble used that relationship to kind of solve this idea and realize, you can see in this picture here, he's pointing out a variable, one of these Cepheid variables that Henrietta Leavitt discovered, and that really placed this galaxy way outside of even the furthest stars measured in our own Milky Way galaxy. So the universe expands as our techniques for measuring and our telescopes expand. And of course, Hubble also, after making the discovery that the island universes of galaxies really were outside our own galaxy, the universe is much larger, also started using the measurements of other astronomers of the speeds of galaxies to identify the relationship of an expanding universe. And we'll be talking more about that in later webinars. So right now, I'm going to take us on a 10-minute or less tour of the realms of our solar system. And this is a key thing. If you're introducing the big, realms of our universe. If you're introducing our place in the universe to audiences, one of the most common misconceptions is this idea that a galaxy, people confuse a solar system and a galaxy because they both are kind of round and flat, and a galaxy looks like the you know, in all the, if they learned anything in middle school or high school about the development of the solar system, it might look like a developing solar system. And in fact, this was the idea of astronomers until this problem was solved. So it's not that that's a naive idea. It's a reasonable idea, but it's a misconception about the actual size and scale. So I'm going to take us on a little size and scale tour. Before I do that, just to highlight the let me see, highlight the poll from earlier in terms of our underestimation of the size and scale of the universe. I'll bring up the results from our little Earth, Moon, and Star if I share the results here. So I don't know if you can see on the screen, but there were these four, for those of you who can see the poll, there were these five pictures of what might represent an Earth and a moon to scale. And it's actually the fifth one where there's a little dot way across the, way, in fact, 30 Earth diameters away, which best represents the scale of Earth and moon. And so people's ideas of the scale of the distance between objects right close by is underestimated. So our ideas of the scale of the larger universe also get underestimated. In the second question, where it says 2 grapes would make a good scale model of the sun and a nearby star if they were separated by, and you have the options of a foot, a yard, 100 yards, a mile, and 100 miles. And actually 100 miles is the correct answer. So a grape, if you think of a grape holding in your hand, the nearest, and that's the sun, the nearest star to that grape would be about 100 miles away. So the stars are really far apart on the scale. So let's take our tour. So again, to reiterate, it's often a good idea to find out with audiences when you're engaging them about galaxies to make sure they understand that the place of a solar system is a very tiny place inside a giant galaxy. Now, galaxies themselves, while the stars are, 2 grapes 100 miles apart, the galaxies themselves are actually relatively close to each other, and we'll see that in a model, an analogy I'll give in a minute. I just want to check and see. Erica, be sure to interrupt me if there's a chat. I see that there's stuff going on in the chat if there's a question. So, so these are all, again, images of galaxies captured from the Astro Pics site. But you can see if you have two galaxies that are the size of compact discs or DVDs, unlike the grapes that are stars, two compact DVDs would be about 8 feet from each other. So maybe an arm's length, your arms apart. So galaxies are relatively close to each other, but the stars inside of them are so far apart that two galaxies could actually collide, and not many stars would collide. Two galaxies could pass right through each other, and the stars are so far apart. So that's kind of a wild idea. You have to kind of sit with that one for a while, and it's always, that may be something we want to ask Gabe about later, if I'm right about that. To construct a mental model of the universe, Tim mentioned that universe discovery guides. There's some great models to present to people to highlight this idea that we live in a city of stars, but we're right in the middle of it, so we can't see the city from the outside. We see it from the inside. We see the Milky Way from the inside, and this is what it looks like. It's a band of stars. If this image, you should really wrap it around your head, because the left side of the image meets the right side of the image in a circle here. And so because the solar system sits in a place kind of not in the middle of the galaxy, but out in the suburbs, we look into the middle of the galaxy and we see the bright lights near the center of the galaxy as we look at the Milky Way. Likewise, here's a picture of London from the outside, right? But we can't see our own Milky Way from the outside because any image of the Milky Way is always an artist's representation, and this is something to make sure visitors understand when they see images that are labeled the Milky Way, that's not a photograph. Whereas this image of another galaxy similar to the Milky Way is an actual image of galaxies that we can see from our place inside the Milky Way. So if you wanted to use an actual size and scale analogy, if the Milky Way galaxy were the size of North America, imagine a quarter in your hand, like if you can just hold a quarter in your hand right now, and you that would be the size of the solar system, maybe out to a Pluto. And the sun would be a microscopic dot on the ear of Washington at the center of that quarter. And so, the stars are, and imagine a grain of sand as a big star. Our sun isn't that big at this scale on a quarter, but if you imagine the stars were all roughly a grain of sand in this North American Milky Way, they'd all be a couple of football fields apart. They'd be very far apart. So this analogy and this image that I'm using are also in those universe discovery guides. Here is another solar system recently discovered, where if our solar system is the quarter, this TRAPPIST solar system, and with a series of 7 exoplanets, would actually fall in our solar system way inside the orbit of Mercury. So again, understanding size and scales of all these NASA's universe of discovery and NASA's universe of learning discoveries, there are lots of analogies you may want to use, helping people understand where these discoveries fit into the realms of the universe. So our Milky Way Galaxy has some 300 billion stars, about 22 billion of them, similar to our own sun, but a lot cooler, and a lot, many are cooler and smaller than our sun. And then a few are bigger and hotter than our sun. And if we, if we identify, I meant to print out my notes, but so you can actually place objects in the universe, like the Eagle Nebula, at this size and scale, where, let's say, the solar system is a quarter in Dallas, Texas, then some of these other objects in our Milky Way that the Hubble takes images of would be, here, the Eagle Nebula is like the size of a shopping mall, and it's a few hundred miles away. I don't actually have my notes, so I know it's in the notes of this slideshow. By the way, all these slides will be available on the community of practice. So the Pleiades, a little star cluster, compared to our solar system quarter in Dallas, Texas, would be about 10 miles away, a cloud of gas and dust and a few great big hot stars. And it would be like the size of a shopping mall. The Orion Nebula, a big star birth region. Here's the Hubble image, again, available on Astro Pics, would be 40 miles away from Dallas, Texas, and almost a mile across. Again, I'm going to kind of go through our slideshow rather fast. Some of the globular clusters that there are gorgeous images of, again, from Astro Pics and from NASA telescopes. These would be up there in Nebraska, quite far away at our North American Milky Way scale. And so this idea of the size of the galaxy to the size of the solar system can help you place these objects in space. So I'll just go through a few of them here. The center of our galaxy, this is a Chandra X-ray image of a flaring area in the very center of the solar system, of the Milky Way. And so again, that's up here near the Platte River in Nebraska, as viewed from a telescope out here in the suburbs of this North American-sized Milky Way. As I mentioned earlier, if the Milky Way is the size of a CD, Andromeda would be about 8 feet away. And those movies that Tim showed at the beginning of the resources, the 3D, this is a Hubble Deep Field. In fact, these galaxies are way outside of our own galaxy, and they're at all different distances from us, from millions to billions of light years away. So that 3D tour, I think we took that at the beginning, right? So I don't need to go to that. And so I've taken you on the lightning tour out to the farthest galaxies. And it's those farthest galaxies that our guest subject matter speaker today actually studies. And so I think I'm going to stop my share so that Gabe, you can start yours and talk about some of these distant galaxies.
Okay, I'm here. Thank you, Mary. Let me get the screen sharing up here. Let's see.
There we go.
Okay, can you see my screen and hear me there?
We can.
Okay, excellent. So yeah, I'd like to just extend a little bit upon what Mary was just explaining in these models for understanding the scale of the universe, and talk a little bit about sort of the largest scales that that are currently observable, really the horizon of our observable universe that we can observe with the Hubble Space Telescope on the left, which is orbiting now. About 600 kilometers above the surface of the Earth. And then I'll talk a little bit about what we can hope to see with a successor to Hubble called the James Webb Space Telescope, which is due to launch perhaps in 2020, coming up soon. So to orient you with Hubble, I think Hubble is amazing. I think it's amazing how many people just know what Hubble is and some of what it's done. My kids' kindergarten classes and things, the kids know what Hubble is, but they don't know, of course, in detail what it does. And so I'll just say a little bit about it. So on the picture here in this first slide is comparing these two telescope facilities. And so Hubble is there on the left, in the sort of bottom part of the tube, kind of by where the NASA label is there, is a large 2.4 meter primary mirror for Hubble. That's what collects the light, focuses it to make the images. And then to give you a sense of scale is this kind of floating school bus that you can see up there. So Hubble is about as big of a school bus. So that's as big as it could be to fit inside the space shuttle bays. So Hubble operates at ultraviolet or UV, optical, and near-infrared wavelengths with a suite of instruments. And as I said, it's orbiting in low Earth orbit, so about 600 kilometers above the surface of the Earth. And so by contrast, James Webb is different in a number of ways, primarily being that it's just quite a bit bigger. It has a 6.5 meter diameter mirror, so it's about not quite 3 times the size of Hubble. And just that large area gives you more collecting area, more sensitivity to detecting very faint sources. It's also optimized for infrared wavelengths, so longer, redder wavelengths, in most cases longer than what our eyes are sensitive to. And I'll say a little bit later on why that's important, both for observing nearby objects, but also these very distant objects. And it'll have a different orbit. It's going to be at a sort of special place in the solar system, what's known as the Sun-Earth L2 Lagrange point, which is sort of this special point where the various components of the gravity of the Earth and the Sun cancel out, and it's about four times farther away than the orbit of the Moon. So it's orbiting way out there in cold space, and that's also important because the mission needs to be very cold. So I have a link there, which you might you could check out sometime if you haven't seen it already. There's a YouTube video of the deployment of this telescope. It's a rendering, of course, it hasn't deployed yet, but it's a pretty spectacular visualization of how this mirror is going to unfold after it's sort of folded up in its rocket launch vehicle. Okay, so let's see. And so on the left here is, I think, one of the more iconic pictures that Hubble has taken. This is a field of the sky called the Hubble Ultra Deep Field. And when we say deep, that means that you stare at a position in the sky for a very long time. And this is a very tiny region on the sky. It's sort of much smaller than your fingernail if your hand outstretched at arm's length. So a very tiny patch of the sky. But if you stare at it with Hubble for a very long time, you find that that's not actually empty space at all, empty regions of space. It's full of galaxies. And so you see all these objects in this image. Most of them in this image that you see here are very distant galaxies. Occasionally there might be a bright star in our own Milky Way, but that's sort of in the foreground. And so all of these different objects that you see here are projected on the surface of the sky, and they're all at very different distances. So generally speaking, the larger objects are more nearby, and then the sort of tiny little faint dots are the more distant objects. And I'll say a little bit later on how the color of the object actually gives us a good indication of their distance. And that's building a little bit on what Mary said at the beginning, and the expansion of the universe that Edwin Hubble, the person, discovered along with others 100 years ago. And so the image on the right there is a simulated image of what we expect James Webb might see. And so to the untrained eye, it might not look particularly different. You know, it's still a kind of a blank field of sky filled with galaxies. But in reality, it is a kind of a fundamentally different image. You can kind of get a sense that there are a lot more objects there. That's just because, again, this bigger mirror allows you to see more and more of these very faint things, very distant things. And the wavelengths that you're looking at are also very important. So some of these objects might actually be more distant than even, in this simulated image, might be more distant than even Hubble could see. And I'll explain a little bit why that is in a minute here. Okay. And so I mentioned how the larger JWST primary mirror gives you this increase in sensitivity just because you're collecting more light, kind of like a big light bucket. But the big mirror also gives you improved spatial resolution, so you can see finer structure in these different distant objects. And so on the left is a image that Hubble might see of a distant, moderately distant galaxy. You can break it up into its component parts and kind of get a rough idea what it looks like, what sort of the different pieces of it are. But with James Webb, you have about a factor of 2 better than spatial resolution, so you're actually able to see individual star-forming regions where stars are actively forming in these distant objects, for example. These are images taken by Hubble of the Eagle Nebula, kind of another iconic Hubble image. You might be most familiar with the image shown on the left there, which is what it looks like at optical wavelengths. So you see this gas glowing. Sorry, Tim, were you? Oh, okay. You can see the gas glowing there, and you see these dark gas clouds there and a few stars. But if you kind of look at this same region of the sky with infrared instruments, or infrared eyes, if you want to think of it that way, this feature, this nebula, looks very different. And at the simplest level, the infrared basically sees through all of this gas and dust, and that's why you can immediately see so many more stars. You're just seeing through this screen of the nebula. And so that's important for what we want to observe with nearby galaxies as well. Galaxies themselves are full of gas and dust, and in many cases that gas and dust obscures starlight, obscures light from actively forming stars, for example. And so James Webb is going to kind of give us this view through all of that obscuring material. And how we actually estimate the distances to these galaxies in fields like the Hubble Ultra Deep Field is a fairly simple concept, and it's related to this observation that Mary mentioned that Hubble himself made, that the universe is expanding. And so in this expanding universe, the light that comes from these various distant objects in some way is kind of stretched because the space that it's traveling through has been stretched. And so the wavelengths of light that become longer means it becomes redder. And so generally the more nearby objects are these larger bluish things that you can see on the left. And the most distant objects are, they're smaller because they're farther away, but they're also redder because their colors have been reddened by basically the expansion of the universe. And so when you take an image with like the Hubble Ultra Deep Field, it's a general rule of thumb that holds up pretty well, that the more distant objects are the redder ones that you see in the image. And that's in many ways exactly how we estimate the distances. So how this works in practice is that you observe an image like the Hubble Ultra Deep Field and many different filters, so specific wavelengths, blue, yellow, green, red, for example. And then you just compare the brightness of of a given object in those different filters. And so what I'm showing here is that as you look towards redder and more distant objects, galaxies start to disappear at the bluer wavelengths. They drop out, we call that, of the bluer wavelengths. And that's again because of the red shifting of their light caused by the expansion of the universe. And so the current sort of limit, if you think of it that way, of what Hubble can see is pretty much the reddest object that Hubble can observe. And so what I'm talking about here, that's defined as being an object that's only detected in the very reddest filter that Hubble can observe with. This is in the infrared wavelengths. And that is an object, the current record holder is an object called GNZ11. It's a kind of an arcane name, but refers to the field of the sky where it was discovered. And so that object is only observed, again, in this very red color that Hubble can see. And it's at a very extreme distance. And so it's at a distance of about 13.4 billion light years. So the light that left this galaxy left it about 13.4 billion years ago, which is only about 3% of the time after the Big Bang compared to the age of the universe now. So 97% of the way back to the Big Bang. And you can see some of the stats here. I'm comparing this early galaxy, this sort of infant galaxy, to our own Milky Way, which of course we live in now. And so it has very different properties. Its radius is about 2,500 light years, which sounds large, but the Milky Way is actually much larger than that. It's 25 times larger than this early sort of building block here. Its mass in stars is 1 billion times the mass of the sun. So again, that's a lot of stars, but these objects that we observe very distant, they merge and they combine and they form stars, after we observe them, to grow into objects like the Milky Way. And it's also forming stars at a very high rate, 25 times the mass of the sun per year, which is 50 times higher than our own Milky Way. So these are very active early stages of galaxy evolution that we're observing here. So the problem, though, with Hubble is that galaxies much more distant than this object GNZ11 become completely invisible to Hubble, just because all of the light of these distant objects is redshifted past where Hubble can observe. And so this is what we call these cosmic dark ages, which are these very early times when the first stars and galaxies are turning on. And only James Webb and other missions, but James Webb will be very good at this, that is observing at longer wavelengths, will be able to detect these objects and see them. And so not only with the images like I've shown before, but one of the real strengths of James Webb is that it will also be able to take spectra. So spreading out the light from these objects into its component parts. And this cartoon here is showing one of these spectra, which is a measure of how bright an object is as a function of the observed wavelength. And then that spectrum tells you many things about the actual physical characteristics of the galaxy. Different parts of the spectra tell you different things. So for example, what are the constituents, the heavy elements like neon and oxygen and helium and other things heavier than hydrogen. It tells you about the motions of gas and stars in the galaxy. It tells you something about, what is the past star formation history of the galaxy. So all these things we can learn from the spectra, which just with Hubble now, this is really not really feasible to do this in much detail of these distant objects. But just to summarize, I want to just give these sort of various properties of these distant galaxies in the very distant universe that we can measure now with Hubble. So the things that we can do well with Hubble are shown in green. That's really just, you can measure an object's distance roughly and its brightness. But we don't know much about its detailed shape and morphology, how its star formation activity, what these objects are actually sort of composed of in terms of their elemental abundances. But all of these things are going to be possible with James Webb, so we have a lot to look forward to there. So I'll pass it back to you. Thanks a lot.
Great, thanks. Thanks, Gabe. That's, I feel like I've been brought to the very edge of the universe and I'm anxious to see what James Webb finds out. Do people have questions that they would like to type in the chat box, or you can take yourself off of audio?
So what kinds of objects do you think you would find in the dark ages that would be different from what we see now?
Yeah, that's a very good question. And I mean, to some extent, we expect to find, things like this object, GNZ11, very vigorous starbursts of, the first stars turning on. There's some current theoretical ideas that suggest that the very first stars that turned on after the Big Bang, they have this name called population 3 stars, but these are stars that formed out of essentially primordial material before there was anything other than really hydrogen around in the universe. And so those are thought to be sort of very distinct from anything that we've observed, observed later. And so galaxies that are composed of these sort of very first generations of stars, these are very massive, very luminous, very, very bright stars. So that would be something that could be sort of fundamentally different than we've seen before.
Would this be the realm of quasars, or am I going in a different direction?
It's a little different. We don't quite know when the first quasars sort of turned on. So quasars are typically supermassive black holes in the centers of galaxies with masses of millions or even billions of times the mass of the sun. So that's a little different than these population 3 stars. These stars might have masses of maybe 100 or a few hundred times the mass of the sun. But it's a very good point that we also are looking forward to having a much better understanding on when these quasars and supermassive black holes formed, which we don't have a very good understanding of currently.
Great. Other questions? Well, Gabe, I want to thank you and let people know also that, should you be starting to think about programming that's introducing audiences to these ideas of what we're discovering about the very farthest reaches of the universe and the new telescopes and technology we're using, and you have questions that you remember, oh, I had a presentation from Gabe Brammer and he could probably answer this question. Your participation in this community of practice lets you keep asking those questions and we can help get answers even when the questions come up later. So, all right, I'm going to.
Oh, it looks like there was another question in the chat box there.
Yep.
If the red-shifted galaxy light took 13.4 billion light years to reach us and is accelerating, how far away is it now?
Gosh, let's see. I think it's more or less that is the distance between us and the object. I mean, the acceleration is a minor detail, but it's roughly, something of similar to that. It's not a very bit different number. But it is certainly true that the galaxy sort of today will look very different than it does as we observe it. It might look like something. It might have been a small building block into something, a galaxy like our own Milky Way, which would be very different than we observe it now.
Yeah, this is Brandon. I also wanted to build off that point, which is that what Gabe is talking about in this talk is really the observable universe and how far back you can look. And as you look farther away, you're looking back in time. But of course, the universe has been expanding this entire time. So those galaxies that we observe are going to be very far away, from when the light, from the early universe, because the universe is expanding.
Yeah, so
I don't know. Go ahead.
So if you could magically, which you can't, and that's the whole thing about observing the universe, but if you could magically, instantaneously be at the position of this modern galaxy and where it is today, which is 13.4 billion years later than we see it, that instantaneous difference in position would be, I think there's some calculation you can do for that, but we can't see that, right? It would be much further than 13.4 billion years because the universe has expanded. It would be, I don't know, something like, I think there's some calculation you can do, but 50 billion years or something like that. But of course, that's the whole thing about the universe, is that space and time, we can only observe what's had time to reach us. So, and that means we can only observe the farthest galaxies as they were billions of years ago.
Yeah, there are resources online, things that are called things like cosmological calculators, where you can put in the number of redshift and out pops various things. But I do caution that if you try to use that, some understanding of the parameters of that is really important, because we are still trying to understand some of those parameters of the cosmology of our universe. And so if you put in some different options, you're going to get vastly different numbers. But Gabe, correct me if I'm wrong, but I believe the sort of common cosmology that we all use today is something called a lambda CDM cosmology.
Yes, that's right.
Right.
So,
you don't need to know what that means, other than if you do Google and look for these cosmological calculators and you see that as an option, that's sort of the common one, that the lambda CDM model.
yeah, I could just make one last comment, which is when we talk about galaxy redshifts, the redshifts have numbers like 1 or 2, and this GNZ 11 has a redshift, we call it, of 11. That's how related to the measurement of it. But that actually has a kind of a direct implication that the redshift is equal to sort of the expansion of the, like 1 over the expansion or the size of the universe at that time. So when the universe now is 1 plus the redshift times larger than it was when we observed it. So 1 plus 11 is 12. So the universe at the time when this galaxy that we're observing it was 11 plus 1 or 12. It is expanded by a factor of 12 since then. So that's just something to keep in mind.
Ah, excellent. Well, so as you'll see on the screen, October 17th, we'll be talking more about this idea of looking out is looking back in time. And in 2 weeks, we'll be talking about the this idea that looking across the spectrum, infrared as well as optical, and X-ray and other wavelengths as well, gives us a more complete picture and understanding of the universe. So we hope you'll come back in 2 weeks. And the next steps are, if you have questions, feel free to put them on the Moodle community of practice. If you don't know what I'm talking about when I say that, make sure you can send an email to Erica, and she can make sure you get on that online site for us. These slides are on that website, so you can look up all these resources and start thinking about how you might use them with audiences. And then in 2 weeks, as I said, we'll be talking about understanding the electromagnetic spectrum. So I think
I'll make one last mention that if any of you guys are at the Association of Science Technology Center Conference, feel free to look us up. There's going to be a booth there. We'll be around the conference as well. But both Mary and I and Brandon will all be there. So if you want to chat, please do.
Great. Thank you all. And we look forward to continuing the conversation.
Thank you, everybody.